What if a machine could learn to create entirely new content, so realistic and detailed that it's almost indistinguishable from the real thing? This isn't the stuff of science fiction. It's the reality of generative adversarial networks, or GANs. The inception of generative adversarial networks, commonly known as GANs, took place in the exciting era of the early 2010s, a time when machine learning was on a fast track of evolution. Introduced in 2014 by Ian Goodfellow and his team at the University of Montreal, this groundbreaking concept involved two neural networks, a generator and a discriminator, operating in a competitive setting. The generator's role was to create new data, while the discriminator was responsible for assessing the authenticity of this data. This competitive dynamic compelled the system to constantly enhance its performance to a point where the artificial data created was nearly indistinguishable from real data. This marked the dawn of GANs, setting in motion a rapid evolution in the field of machine learning. In the progression of generative adversarial networks, a crucial breakthrough occurred in 2015 with the development of the Deep Convolutional GAN, commonly known as DC-GAN. This revolutionary model by Radford, Metz, and Chintala introduced the application of convolutional layers to both the generator and discriminator aspects. This advancement was indeed a game changer, as it empowered GANs to produce more intricate and comprehensive images, marking a stark enhancement from the original model. Conditional GANs, introduced in 2016, marked a significant advancement in the concept of generative adversarial networks. This variation empowered the generator to produce distinct types of data, influenced by a specific condition or tag. The impact? A shift from GANs generating mere random imagery to producing specific content with a clear context. In the year 2017, the domain of artificial intelligence was invigorated with the introduction of the progressive GAN by Karras, Ayala, and Lane. This innovative model revolutionized the training process of the discriminator, initiating with simple low-resolution images and progressively gaining complexity in stages. The introduction of progressive GANs bestowed significant benefits, including substantial improvements in the quality of the images generated and an enhancement in the efficiency of the training process. BIGAN, introduced in the year 2018, was a pivotal development in the realm of generative adversarial networks, or GANs. This technology utilized larger models and harnessed greater computational power to produce high-resolution, superior quality images. This pivotal moment in GANs' evolution indicates their capabilities in generating astoundingly authentic content. As we look towards the future, the evolution and improvement of GANs are set on a promising trajectory. The potential applications of GANs are immense and predominantly unexplored. They hold the key to creating hyper-realistic human faces, synthesizing seamless speech, and even forging new molecules for drug discovery. The extent of their potential is enormous, opening up new frontiers in numerous fields, and it is an exciting time to imagine and explore what lies ahead for GANs. As we continue to delve into the fascinating world of GANs, let's take a moment to explore their impact on the field of art and design. GANs have the unique ability to generate creative designs that are not only unique but also captivating. Imagine a machine learning model that can conjure up a myriad of designs, each one distinct and innovative, all at the push of a button. Through the power of GANs, we are already seeing the creation of digital artwork that is so intricate and aesthetically pleasing that it's challenging to tell whether it was created by human hand or artificial intelligence. Artists are now collaborating with GANs to push the boundaries of creativity, resulting in stunning pieces that blur the line between technology and art. Moreover, in the realm of design, GANs are revolutionizing the way we approach creative tasks. From generating unique pattern designs for textiles to creating innovative architectural concepts, GANs are proving to be an invaluable asset. They are not just tools for replication, but also for invention, inspiring designers to think outside the box and enabling the creation of things that were previously unimaginable. However, it's important to note that while GANs have opened up new avenues of creativity, they also raise questions about authorship and originality in the digital age. As we move forward, it will be interesting to see how these issues are addressed, and how the symbiotic relationship between human creativity and artificial intelligence evolves. Our exploration of GANs would be incomplete without discussing their transformative impact on the gaming industry. Game development is a complex process that requires a blend of creativity, technical skill, and often a considerable amount of time. However, with the introduction of GANs, this process is being revolutionized. Imagine a world where game environments can be generated autonomously by artificial intelligence, creating vast, detailed, and realistic landscapes that were previously only possible through hours of painstaking design work. With GANs, this is becoming a reality. These networks can generate terrain, buildings, flora and fauna, and even weather conditions, all based on the data they've been trained on. This not only speeds up the game development process, but also introduces a level of diversity and realism that was previously unattainable. But it's not just the environment that GANs are enhancing. They're also transforming the way we design the characters that inhabit these worlds. GANs can generate a wide variety of realistic characters, each with their own unique features and attributes. This means we can have a more diverse range of characters in games, enhancing the immersive experience for players. However, just like in art and design, GANs in gaming also raise questions about creativity and originality. As AI becomes more involved in the creation process, it will be intriguing to see how the dynamics of game development change and how the gaming community adapts to these changes. In the next scene, we will conclude our discussion on GANs, summarizing the incredible journey these networks have embarked on and looking ahead to the exciting future they promise. As we delve deeper into the practical applications of GANs, let's turn our attention to an industry where their impact could be life-changing: healthcare. In the realm of medicine, patient data is invaluable. It's the foundation of research, diagnosis, treatment plans, and even the development of new technologies. However, real patient data is sensitive and subject to many privacy laws, making it challenging to access for research and training purposes. This is where GANs come into play. Imagine being able to generate synthetic patient data that is statistically similar to real-world data, but doesn't compromise any individual's privacy. GANs can do just that. By training on existing patient databases, GANs can create detailed, realistic patient profiles, complete with medical histories, symptoms, and even genetic information. This synthetic data can then be used in a variety of ways, from training medical students to developing new treatment strategies, and even in the creation of more personalized healthcare plans. Moreover, GANs can also simulate the progression of diseases within this synthetic patient data, enabling researchers to study the impact of different treatment options over time. This could potentially lead to breakthroughs in understanding and treating many conditions, ultimately improving patient outcomes. However, as with any technology, there are potential pitfalls. The accuracy of the generated data is only as good as the data GANs are trained on. Therefore, any biases in the original data can be reflected in the synthetic data, potentially leading to skewed results. Therefore, while GANs offer immense potential in healthcare, it's crucial to approach their use with careful consideration and rigorous validation. As we move to our conclusion, we'll reflect on the incredible journey of GANs, from their inception to the myriad of applications they have today, and the transformative potential they hold for the future. Wrapping up, the voyage of generative adversarial networks since they came into existence in 2014 has been a narrative of swift progression and novelty. Commencing with Goodfellow's initial idea, through to the unveiling of DC GANs, conditional GANs, progressive GANs, and Big N, each landmark has symbolized a considerable progression in the competencies of these potent machine learning instruments. As we gaze into what lies ahead, the prospective applications of GANs are nearly infinite, prophesying a time where machines can fabricate content that is nearly identical to reality. Perhaps one of the most promising applications of GANs lies in the field of drug discovery and development. Leveraging their generative capabilities, GANs can create new molecular structures that could potentially be used for novel drugs. Furthermore, these networks can predict the effectiveness of these drugs by simulating their interactions within the body. This not only helps in accelerating the drug discovery process, but also in reducing the overall costs associated with it. Thus, GANs are poised to revolutionize the pharmaceutical industry, promising a future where effective treatments can be developed faster and more efficiently than ever before.